Hello, everyone. Welcome to Minitab webinar, Harness the Power of Predictive Analytics for Statisticians. My name is Ming Dong. I'm one of the solution architect in Minitab office, Sydney. And I've been working with Minitab for 17 years. And I'm here to support customers in Australia and also APAC region. So I'm going to present this topic. Let's share the knowledge. So for bandwidth reasons, I'm going to turn off my camera so I can focus on the topics. Okay, so let's talk about predictive analytics, which is the next step on your analytic journey. Because before we have descriptive step, like talking about graphical analysis, and diagnostic analysis, like hypothesis testing. This is what we've done before. But as we have more and more data, and we try to get more and more value from our data, we're going to think about a new tool or new approach we call predictive analytic tools. So predictive analytic tools or the algorithms, it's kind of a combination between classical statistics and machine learning. So we say predict analytics is a form of advanced analytics, but we like use current and historical data to forecast activity, behavior, and trends. So it's a combination of traditional statistics we learned before, but also we can combine machine learning algorithms. So for example, if I try to predict a lifespan for a tile, I might collect data, something like the age of the tile, rubber compound, and the temperature, and terrain, and speed driven, and maybe some like a weight carried. All these variables, then I can calculate or whatever apply algorithm, we can predict the lifetime, right? Okay, here is a list of architects behind the Minitab predictive analytics and machine learning algorithms. For example, we have Dr. Jeremy Friedman, who is a professor of statistics from UC Berkeley. And also we have Dr. Leo Brinkman, who is a professor of statistics from Stanford. Their paper were cited in hundreds of thousands of academic and professional journals. Minitab algorithms such as CART, MARS, Random Forest, and TreeNet have won many awards and achievements, including PAKDD, which is Data Mining Competition, and DMA, which is Direct Marketing Association Analytic Challenge. And also KDD, the Annual Data Mining and Knowledge Discovery Competition. Okay, let's use a simple example to illustrate the algorithm. Let's say we have many dogs and many kind of dogs and many kind of cats, right? We try to classify which is a dog, which is a cat. So first we check lifespan, longer than 10 years or less than 10 years. If it's longer than 10 years, then we're going to ask, does it bark? If it's yes, it's less than 10 years. If it's less than 10 years, we're going to check, does it bark? Yes, it's a dog. No, it's a cat. If lifespan more than 10 years, which is on the right-hand side, So we're going to check, does it have sharp claws? If yes, we say it's a cat. If no, it's a dog. So it's a simple algorithm, like a binary decision tree to classify dog and cat. Okay, when we come to machine learning, suppose we have 200 variables, 10,000 rows, which is a huge data set. When we do machine learning calculation, we'll always separate data set into two parts, just randomly separate. For example, 7% we use for training data, 30% we use for testing data. So training data, the purpose for training data, we try to create a model, which create an algorithm result. But for the testing, we use to check, or we say assess the model. If the model is good or bad, you try the test data set. Then you probably want to ask why we want to test, why we that you don't use the whole data set. Okay, so we have two different kind of problem. One is called bias, high bias, another is called high variance. What does it mean? So if you build a model, very simple model, for example, a straight line, right? We'll talk about regression, using regression as an example. A simple line, which is very simple model, straight line. Then the predicted value and the actual value, there's some difference. And this difference there is looks like big, like look at linear regression, just one line, and difference is big. We call this high bias, which is kind of error. However, to the extreme, let's build a very complicated model. So cubic could be one, or could be even more complicated. Or we say we follow the dots, all the dots, right? We can have a model which follow all the dots, which means for sample data, no problem, everything got covered. But if you have new data, like a testing data, then you're going to see a big difference between predicted value and actual value. We call this high variance. So we say, if you look at the graph on the right, when the model gets more complicated, our training data set always produce, like the error part can be reduced, always reduced, right? Look at the red line. However, when the model gets more complicated, when we get new data to test it, then we're going to have big variance. So, which means in the beginning, if you look at the test data curve for the error part, in the beginning, the more complicated, then the error goes down. But after a certain point, then the test error will go up. We call this overfitting, which means you fit the model too much, the tester, when we have new value, then you're going to have high variance. So we need to find some point in between, not too complex, not too simple. So that point is kind of model we're looking for. That's how we use a test curve to find out where it is. Okay, let's try to understand the basic of classification problem. So we have a problem. We want to predict the machine failure. This is a turbine, big turbine. So we try to capture the problem before things blow up, because if they blow up, it can be a huge cost. So we try to capture under different conditions, I can predict the failure, hopefully. So the problem is a binary classification problem, because if you look at the column 5, C5 will have failure. 0 stands for no failure, 1 stands for failure. So response is going to be machine failure, 0, 1. The predictor is going to be like air temperature, rotation speed, torque, and temperature, whatever. So these are the called predictors. Here's the data set. You may have tens of thousands of rows. Okay, so let's see how Minitab run this. So I play a very like 30-second video, just show you how Minitab can run this. Yeah. So go to predict analytic module. We go to classification. Yeah. And response, I'm gonna key in machine failure because of 1, 0. I'm looking for 1, which is failure. I'm putting all the continuous predictors. And if you look at the validation, we use a test data set, right? 30% for testing, and other 70% for building a model. That's it. Then Minitab can generate output. Okay, so let's look at the output. So running Minitab, very simple, just click, everything done. Okay, here's the output. So the tree, a diagram on the left shows number of terminal nodes, which means that look at the tree, how many terminal nodes. Here looks like the number of terminal node is 6. It's just like based on the misclassification cost. It's like actually misclassification cost. Then we find out which is an optimal point. So the tree the algorithm tells me the number of terminals 6 nodes, which is the size of the tree. Then the outcome based on the ROC curve, which is on the ROC curve area, is about 84%. And also the diagram in the bottom tells us that torque and rotation speed, these are the most important variable, then followed by air temperature. So this graph tells us, okay, how big is the tree and the accuracy, because they are based on ROC, and what are the key variables related to the failure. Then we look at the tree. So at the top, because we use 70% to build a model, right? So we say percentage of 1, which is failure, is about 3.5%, which means overall failure rate about 3.5. But it's separated into 2 parts based on rotation speed. If it's less than 1386 and higher than 1386. So we can see simply from here, if the rotation speed is, let's say, if it's less than maybe roughly 1,400 RPM, then the failure rate can increase, jump to quickly to 15%, which is you can see from the diagram. So very simple, rotation speed high or low, the failure rate is different. If it's less than 1,400, the chance of failure increase to 15%. Then we study further. Let's go to the left-hand side, because left-hand side rotation speed is low. Then we look at air temperature. So if air temperature is above 300, so that's this part, above 300. Then the chance of failure increased to 38%. Wow, that's another rule we need to understand. By chance, it's only 3.3% something, but now it's 38%. And also we have a track. You can see that if with low speed, which is on this track, and torque, if it's above 53, whatever the unit, then the chance is 14% as well. Again, based on the average 3.5, this is also very high. So this is our rule number 3. Maybe we want to look at the right-hand side of the tree, which is the rotation speed is higher, right? Higher than 1,400 RPM. Now, again, if with high speed, which is on this right-hand side, but if it's torque less than 15.3, the chance of failure, 50%. Very high again, okay. But otherwise, we go to this direction. If torque is, say, with high speed, and torque is about 57, which is terrible, very, very high. Then you could, if you look at the failure rate, 37, more than 3 times higher. Okay, so we learn this from the graph. We can see the conditions, under which conditions, what about the failure chance, and the overall, we say we have different rules. Okay, several different dangerous rules we need to be careful. Because talking about a turbine, a big wind turbine, costs about 2.4 to 4 millions, very, very expensive. So if we can identify the chances of failure, so which means you can save a lot. We can try to fix it instead of see its failure. So based on the model, 84% of, talking about the model performance, 84% of failures we can accurately predict it. So we call this based on ROC, we can 80%, 84% we can predict. So something probably someone gonna ask, is there any chance we can achieve high accuracy, right? Better accuracy, hopefully we can getting better, but save more money. Yes, we can. So this is a typical question. If you have a problem, you may ask for expert, right? Expert A give you a question, give you an answer. But if you just follow one expert, he could be wrong, right? The expert could give you a wrong answer, which is end up with disaster. So we say an expert is a person who makes only serious mistakes. Okay, if the expert is wrong, so you have a big problem. If you just ask one expert, then we try a different approach. We ask many experts, right? In this area, we definitely have many, more than one. We have a few hundred experts. We ask their opinion, right? So we collect those opinions, then we decide. Could be decided by average or be decided by the voting, the majority. So these are different approach. The second algorithm we're going to introduce is called random forest. It's based on we are asking many experts. We call it ensemble trees. So this algorithm can generate multiple trees, but they are independent. Independent means they're not related. So we're going to introduce, like when we build a model, we're going to use subset of features and subset of variables, which means we're not using all the variables to build a model. We may use a proportion and also proportion of data. So this is like independent tree. So just like a sample variables and also features as well from the data. Then we build multiple trees, many trees, maybe a few hundred. So at the end, we decide yes, no. We base on majority. If 300 trees, 200 say yes, 100 say no, we go for yes. So let's see how Minitab perform random forest. Okay, just go to random forest classification. Again, you put in the variable response as failure. Yeah, looking for one and looking for all the continuous variables. Yeah, we use AutoBag for validation. We build 300 trees this time. Okay, and run it. Then we have the model. All right. So let's see the output. So here's the output from random forest. So you will see that on the graph, you have what we call misclassification rate. Yes, we're looking for low. So you can see the test and auto back, which is like a training and a testing, right? When we come to 300, like pretty close, which is testing and training is very close, which means the model is stable. Look at ROC curve under the area. Now it's 80%, right? And also we see the key drivers, torque and rotation speed, and followed by air temperature. So torque and rotation speed, these are still the majority major key variables we need to pay attention. Okay, so we asked many experts. We can see the performance increase because ROC curve area increasing. Now let's try another algorithm we call TreeNet. TreeNet is a collection of classification regression trees. Yeah. Okay. So when we build TreeNet, we say the TreeNet gonna create nested trees sequentially. So which means you build the trees one by one. So the tree is gonna nest it. We say each tree learns from the previous tree. So when we build a tree, based on what we have done so far, then we build a tree. Okay, which means each tree learns from previous tree. So the multiple decision trees, this model we're gonna have many trees, but every tree gonna learn from each other. So to illustrate the idea, it's just like I use climbing mountain as an example. So if you climb a mountain, you probably have GPS in your hand, right? And then we start from bottom. We set up a direction. Okay, here's the direction, then we go. You follow this direction, but sometimes you lost signal, right? It's possible in the mountain area, you lost signal. Then you go to a wrong direction. Then at a certain point, okay, you got signal. You check. Oops, we go to somewhere which is not supposed to be the right direction. Then you check again, at this point, you already walked this so far, you climbed this so far, and you want to find out which is the correct direction now. Then you have a direction. So this is like first part, we're done. Second part, again, readjust your direction and go. Similarly, when we come to a certain point, when we check again, maybe we're going to readjust the direction, maybe go this way. Okay, then the third part can add on. So each section, just like a tree, just like a model. First section, second section, third section, move on. So at the end, we're going to reach to the end, right? Reach to our target. But every time we build a tree or add a section, always based on what we have done so far. And the tree is going to based on where you are and where is the target. Then we set up direction. Okay, so always you just readjust your direction and set up new tree, always build on previous trees. That's why we call this a sequential approach. This algorithm works very well for high dimension data with complex interactions between variables, and also for non-linear relationships and handle between variables. So here is a TreeNet, right? TreeNet result. Let's see how we go. In this tree, because TreeNet, again, many trees, so we don't have one tree to represent the whole story. We just have a tree, an algorithm, and tell you the performance. Now the performance here is, we can see from the graph, ROC is 89.7, which is close to 90. Yeah. And the important variable, torque, and followed by air temperature and rotation speed. Yeah. So these are pretty close, rotation speed and air temperature. These are key drivers. So you will see if we compare three different algorithms, car give me ROC 84, random forest give me 89, close to 89, and TreeNet give me ROC 90%. So three different algorithms, three different in terms of accuracy. So I'm not saying TreeNet is the best, but sometimes different algorithm perform well, but another algorithm perform not very well. Depends on the data. And the TreeNet also gave us some called partial dependency plot. It tells you relationship between different variable versus the chance of failure. So you can see torque, like if the torque is between 15 to 50, maybe 50, it's very steady. The failure rate is very steady. But if it's under 15 and over 50, they follow different direction, different kind of graph, direction or curve. Similarly, rotation speed. But air temperature is, if it's under 300, very steady, failure rate very steady. Above 300, increase dramatically. And another story between temperature. So this graph gonna give you direction. What should I do next? Because if you try to optimize the torque, optimize rotation speed, you try to reduce the chance of failure, you can do DOE based on these variables, these key drivers, and decide where to set up these variables. This is a follow-up study. We use DOE. Okay, so let's talk about regression. So regression, which means your response is going to be numeric. So let's say I want to predict energy output of a solar power plant, right? Using different meteorology conditions, because we try to prepare the energy generation based on upcoming conditions like a storm. We try to, under storm, how about our energy generation? So different condition, we have energy output. So it's a regression problem. The response is going to be energy, and the predictor going to be all the different conditions, including sun elevations, sun direction, temperature, and cloud cover, and wind speed, etc. So we just run the model. It's a very similar dialog box and very similar as card you saw before. So let's see, because it's a regression, we are interested in R-square, right? Percentage variation explained by the model. So look at the card. We have R-square is 81.72, okay? And the key driver is going to be sun elevation, humidity, and temperature as well. Okay, again, card gonna give you a tree, but this tree again tell you under which condition, how about the energy generated. So again, into different terminal, which is different kind of rules. So we can easily to figure out under which condition gonna give us some the energy generated is low, and also energy generated is very, very high. So for example, if the sun elevation is less than 14.49, all right, the energy generated only 86 units. But if the sun elevation greater than 26.7 and sun direction is less than 240, and cloud cover maybe less than 65%, then the energy generated can be very, very high, something like for 1,451. So you can see the different extreme high, extreme low value, we can identify easily. So this is the model generated from random forest. Again, it tells you the R square. In this one, R square is 87.9. It's improved, right? Card is 82, now we have 87.9 because we generate multiple trees and we predict more better. Increase to 87.9. And sun elevation is going to be still the most important variable and followed by sun direction. Okay, so we try again, we can try tree net regression. It's 88.2, right? So again, it's increased from card 82 to tree net 88.2. This is big jump. And sun elevation going to be the key drivers. So yeah. So we have regression, we have classification problem, we all can handle with CAR, with TreeNet, with random forest. Let's compare, or let's talk about the advantage versus disadvantage. So CAR is a powerful machine learning algorithm. It gives you a simple illustration, like a segment of solutions. So give you a very clear tree, tell you under which condition is a high chance failure or low chance failure, or generate a high volume of Y or low volume of Y. Very clear picture, explain clearly. It works for both classification and regression. And it's discovered based on data driven. This is something I probably say machine learning algorithm, when you run it, it doesn't give you any assumption, which means what's a model equation? No, we don't have model equation. We just look at data to split yes, no. How to split? We based on maximum separate yes, no. So this is something based on data, we split a tree. We don't have any assumption. So CAR can be very easy to interpret. Yeah, makes sense. And also very simple. Emphasize the simplicity. Then talk about random forest tree, which is a kind of group of trees, either sequentially or independently. They are looking for accuracy because you have multiple, looking for prediction, multiple trees, you get results from many, many experts. So the accuracy can be much better. In general, I would say in general. Accommodate all the predictors, yes. And this algorithm works very well for, like I said, we're talking about Y data, talk about genomics and biotech, blah, blah. And also give you partial independency plot, show you the relationship between your key drivers and your Y, right? We'll call this is from TreeNet. But disadvantage is it's based on a black box. You don't see a block, the tree. So you see a black box. It tells you the performance, good or bad, or what's the performance, but doesn't give you the detailed information. And also it may take longer to build because we're talking about building multiple trees, right? So these are the advantage and disadvantage of random forest, TreeNet, and CARD. Okay, so when I try to measure the bed, I'm moving some bed in the house, I might need a meter, right? Just measure. But I'm draw a graph, I'm probably use more accurate, like a ruler, as kind of things to draw a graph. But if you're looking for high accuracy, I definitely need some high precision engineering tools. Yes, correct. different tools for different purpose. So same thing, when we talk about data analytics, we also need multiple tools because you don't know which tool is going to fit your data, fit in different situation. Similarly, that's why we have this card, TreeNet, random forest, and regression, and Mars. These are different algorithms. When you have a data set, you don't just rely on one algorithm. You're gonna look at with different algorithm. Just like you do scan, X-ray scan. You can scan from different angle and look at the whole picture. Which one give you a better understanding? So try different algorithm is the reason why we're going to have better understanding of data. The data set could be varies a lot. We want to see a better picture. Try different algorithm. Minitab also provide these tools called automated machine learning, which means we try different algorithm, including TreeNet, random forest, multiple regression, Mars, card, and maybe some model will give you several options based on the tuning parameter, like learning rate, maximum terminal node. These are the tuning parameters. So we call automated machine learning. When you run this, it normally generate 11 models. So for example, for TreeNet, we may give you 6 different models, and you can choose which one you want, but also we pick up which is the best. So if you look at the TreeNet model, we have this something like star, which say this is the best. So based on R squared, this is the highest. We say this is the best. But you can choose other algorithms as well. Make your life simple. Okay, so I introduced a predictive analytic module, which is based on a large amount of data. But for R&D, for research, in Minitab, we have this called R&D module, which means when you do study, for example, if you're looking for describe your data, what are the tools we can use? If you're talking about fitting model, estimate reliability, these are research topics. We group those tools into one place. Okay, we call this R&D module, may helpful to research people, right? If you in university or research institute. Here, just quick overview of Minitab products. We have Minitab, we talk about the Minitab, yes. Statistical analysis tools. We also have Connect, which can ingest various data from various data sources. And it's a cloud-based product. And also when we bring data into one location, we can combine, we can cleansing, we can get data ready in the right format for Minitab analysis. Okay, so this is Minitab Connect. Also display result live in a dashboard. Model ops is for model deployment. So a model is just like a classification tree is a model. But if I want to put into production, we might need model ops. We also have workspace and we have engage. That's for project management. It's a soft tool, to manage project with different methodologies. Education hub, just learn Minitab in your pace. Watch video is online product. Watch video and learn Minitab and statistics. We have real-time SPC focus on manufacturing, production line, real-time monitoring. All right, okay. This is maybe better explain the problem, better explain the whole picture of Minitab. On the right-hand side is the problem-solving tools. For example, from idea generation to project planning to execution to tools to tracking. So these are project management part. On the left-hand side is data-driven, based on data. Talking about data collection using Connect, talking about statistical analysis using Minitab, talking about predictive analytics using machine learning, PM module, and we talk about deployment, we talk about model ops. So down the line. So this is a whole picture of Minitab products. If anything we can help you, please let us know. Okay, appreciate your time, and here gonna end up the presentation. Thank you very much.